Hi everyone. Today we're delving into the world of welding processes, specifically MMA or manual metal arc, also known as shielded metal arc welding or SMAW in the United States. We're going to cover a brief history of the welding process, how to identify different parts of the process, as well as how to understand MMA electrodes. This is all the information that you need to know if you're completing a qualification like C-SWIP or any other weld inspection quals. So let's get started. Believe it or not, the roots of MMA go all the way back to the 19th century. It all started with the discovery of the electric arc by Humphry Davy in 1800 and the continuous electrical arc by Vasily Petrov in 1802. Sorry if I'm getting them names wrong. Some of them are quite hard for me to pronounce. These discoveries laid the groundwork for what would become modern welding. So doing that work with electricity really kickstarts electric arc welding. So in 1880s, things started really heating up quite literally. Right. In 1881, we had the development of the carbon arc process. And soon after, we then took in 1885, we took another step forward where we had advancements of carbon arc welding, right? But the real game changer came in 1888 when we had the invention of the consumable metal electrode. This was a huge milestone in the process and allowed a leap forward in its use in a more industrial process. By the 1920s, industrialization of the extrusion process made it cheaper and easier to coat these electrodes. This allowed for more complex coating mixtures designed for specific applications. And in the 1950s, the introduction of iron powder into the flux increased welding speeds and efficiencies. So throughout the 20th century, MMA welding technology continued to evolve. The transition from traditional transformers to modern inverters brought better control, efficiency, and welding quality. Despite the rise of other welding methods, MMA welding remains popular due to its versatility, its simplicity, and its effectiveness for a range of applications, including construction, shipbuilding, and really importantly, repair work. So let's have an overview of the process itself. MMA uses a consumable metal electrode coated with a flux. When the electrical arc is struck between the electrode and the workpiece, the intense heat generated melts both the electrode and the base material. That welding arc is around 6,000 degrees Celsius, so the temperature of the surface of the sun. As this melts the electrode in the flux, we produce a shielding gas or evolved shielding gas, which in the main is either CO2 or hydrogen, depending on the electrode type. And this protects the molten weld metal pool from the environment. So the oxygen and hydrogen in the main. This process also forms a slag layer which comes from the flux. So as the electrode flux works to remove impurities, and uses up its additives and its bulking agents and all that type of thing, they're ejected from the material and they form a slag layer. This slag layer is used to help support the weld pool and give us a good profile to our final welds, but also acts as a little bit of a cooling blanket, slowing that cooling rate to a more desirable rate of cooling. So what's the advantages and disadvantages? Well, the main advantages of this system is it's very portable. So where we use a relatively simple inverter set, it means we generally just need to have some sort of electrical power to our welding area. And in the main, these can come on in the UK, 3-pin 240 volt pins, or the blue 240 volt on-site units as well. This makes it very adaptable to go wherever we need to do the welding. Because of this and the cheapness of inverter sets, these systems are relatively cost effective. We don't need expensive computer-aided systems like synergic things and stuff like that for MMA. We don't need shielding gas as a separate input, and we also have reduced operational costs because the maintenance and the likes around these sets are relatively low. But of course, with all advantages comes a series of limitations. So one of the main ones here is slag removal. If we don't clean the welds between passes or at stop-start locations, we run severe risk of slag inclusions, which will fail our welds to most acceptance criteria. The skill requirement is fairly high with this process when we compare it to something like MIG-MAG flux core, because it's a manual welding process. That means that the welder needs to manage travel speed and arc length. This, as you can imagine, trying to move right to left or left to right at a constant speed while your electrode melts away from the workpiece, so you have to adjust that arc length, requires quite a lot of dexterity. We also have a limit on the arc time that we have. As a general number, we're looking at the efficiency of the process being around 30%. So for, say, every 10 minutes of welding, we're only actually got arc on for about 3 minutes. The rest of the time is cleaning, back grinding, setting up our next electrode, and getting ready to start again. So one of the things that makes MMA welding so versatile is the range of electrodes we can use and match different materials, different strengths, but also different welding needs. Do we want something that has a high toughness value, or do we want to weld vertically down and have productivity increases? Or do we want something in the middle and do general purpose work? Well, our three main families of electrodes are going to give us that choice. So when looking at them, we have rutile, basic, and cellulosic electrodes. So let's start with rutile. Now, rutile electrodes are what we refer to as general purpose, general process electrodes. They give relatively good strength, but not really any toughness values to speak of. So they're good for, say, you can use them on pressure vessels and the likes if they're always stay warm, but we like to use them for that maintenance type work. So fairly quick, fairly low risk welds. They arc up fairly easily, and when the flux burns, it produces a carbon dioxide shielding gas. Next, we have basic electrodes. So these are by far what I would refer to as our engineering standard electrodes. They burn to produce a CO2 gas, but because of the alloying content within them, they produce welds with very good toughness values and strength. But of course, the cost goes up when compared to rutile. These electrodes are also much more difficult to start and arc up. And generally, once you've welded partly with an electrode, they struggle to arc again. A lot of people are standardizing around basic electrodes, so you can have one type of electrode on a site and not have to worry about cross-contamination of electrode types. Our final family is cellulosic. Now, cellulosic is used for a type of welding we generally refer to as stovepipe welding. And this is where we weld vertically down on overland pipelines. But any process that you require vertical down welding or very deep, fast penetrating welds, this is the electrode for you. The main issue with this electrode is in order to produce the deep penetration, it burns to produce a hydrogen gas. So that instantly triggers worries about things like hydrogen-induced cold cracking.
Yeah.
We can get around that by having higher preheats, higher heat inputs, or post-weld heat treatment methods to help remove the hydrogen from the welding process and from the final weld metal. However, it's got to be accounted for. So how do we identify these electrodes? Well, in the main, we have two electrode classification standards, one being American and one being European. Right. So we'll start with the American AWS 5.1 first. Okay. In this process, what we have is electrode identifications which have something along the lines of E7018 is how we would say it. Now, these numbers refer to different requirements of that electrode. So starting with E, this generally means a covered MMA electrode, or SMAW if you hear about that. The next block of numbers is our 70, which represents the minimum tensile strength of that weld metal produced. So in this case, we would be at 70,000 psi. If we had a 60 there, it would be 60,000 psi and so on. The number 1 refers to the welding position. So a 1 here means use it in all positions, so flat, horizontal, vertical, and overhead. And our 8 refers to the flux covering and the type of current. So a 70 in E7018 means a low hydrogen potassium electrode suitable for welding with both AC and DC positive. Now, what we have to do here, especially for our inspection qualifications, is know the different numbers for those final flux coverings. So what we have is we have a 0 for cellulosic and a 1 for cellulosic. The next main one is our number 3 for rutile, and then 5, 6, and 8 for basic. There are others, but if you memorize this list in front of us, then anything else that's different, well, you've got a good idea where you are. The way I remember it is we start with the lower numbers, it's cellulosic first, moving into rutile, and then the higher numbers are our basics. The difference in the numbers indicate, for the same electrode type, indicate a change between non-iron powder and iron powder. But you can try and remember that if you want, but I think in the main, if you just memorize the numbers in their flux type, that should be enough for what we need at this point. Now we move on to the EN system. So this is EN 2560. In this standard, what we have is a lot more information when directly compared to the American AWS. Here we have electrode types, which are referred to as things like E46, 4B, 3, 2, H5. On this number we're looking at, we have E, meaning covered electrode. 46 is our minimum yield strength in newtons a millimeter squared. So what we do here is we just add a 0 to that number. So 46 is our minimum yield strength of 460 newtons a millimeter squared. The 4, so our 4 is the minimum impact energy temperature. Now, the 4 indicates tests carried out at minus 40 degrees. The acceptance criteria is generally 46 joules for electrodes. So if you said there was a 3 there, the 3 would indicate 46 joules at minus 30, and so on. B is our flux covering type. So this is where we can just fairly simply identify B for basic, R for rutile, C for cellulosic, and RR is a heavy rutile saw with iron powder added to the mix. The 32 is our welding position and current type. There's also our efficiency of our electrode in there. You go to the standard and you check that out. And then the H5 tells us our hydrogen content. So H5 means when used correctly and baked in accordance with the manufacturer's recommendations or taken from a vacuum pack, this electrode weld metal will have 5 milliliters per 100 grams of weld metal of hydrogen. So when selecting electrodes for our use, we really have some things to question on our selection criteria. Mainly material thickness, welding position, joint type, and welding current. By answering those questions, we can answer, do we want a basic electrode, do we want a cellulosic, or do we want a rutile? We would also maybe answer there the final mechanical properties that we want that weld to have. So if we need toughness values, that's instantly going to push us down the basic electrode. If we're not really bothered and we can get away with just having good tensile material, we'll go with our rutile. If we want to have deep penetrating fast welds, then that will be our cellulosic. So as a recap, we have a welding process which is very versatile. It is fairly cheap and easy to transport because it's fairly small and portable. We have a range of welding consumables that we can use of various different strengths and uses, but they fall into 3 categories. So basic is a high calcium carbide. They provide low hydrogen welds and are suitable for high quality welds with good mechanical properties. Our rutiles contain titanium dioxide, offering a smooth arc and easy slag removal, and they're ideal for general purpose welding. Our cellulosics have a high cellulose content, so they produce high amounts of hydrogen, above 80 milliliters per 100 grams, but they have the advantage of producing deep penetration welds, which can be produced quickly. Right. They're used for vertical down and overhand head positions. So that's it for today's video on MMA welding and the electrode identification. I hope you found this information helpful. If you have any questions on this topic, let us know in the comments below, and I'll try to answer as many as I can, and if required, produce a different video to answer those in more detail.
So thank you for joining me for that video, and if you would like to learn more, remember to subscribe here. But if you want to learn your next bit of welding technology, that's this video here that's appearing on your screen. And as always, stay safe and best of luck with your studies.